All right. Okay, so on Monday, today's Wednesday. Okay, so on Monday we were talking about our hierarchical model, and we talked about the Gibbs sampler, and we spent a lot of time factoring out the Gibbs, factoring out the joint distribution. Here, let me clear up my environment from last class. Factoring out the joint distribution into a bunch of kind of individual conditional distributions. So the model that we have is that we have a few arbitrarily selected hyper parameters. Okay, so we have values like k is equal to 300, a omega and b omega. I think we said is going to be 3 and 7. And in our hierarchical model, we say omega gets drawn from this beta distribution. Omega is going to be kind of the mode of our prior distribution. And so omega gets used to determine what alpha and beta are. Alpha is going to be omega times k minus 2 plus 1. Beta is going to be 1 minus omega times k minus 2 plus 1. And so these shape parameters alpha and beta are determined by omega and our choice of k. And the alpha and beta then get used in our prior distribution. We have the prior distribution for theta. Theta is the player's batting average. Okay, so the player's batting average is, has this prior distribution. And based on that, we will draw a theta sub s. The theta sub s gets used in a Bernoulli distribution, which will determine the hits and the misses of an individual player. Okay, and we've got S different players. So each sequence of hits and misses, is player specific. And it's going to be theta S here. All right, and so that's kind of our hierarchical model. Here's kind of a diagram from the textbook, and it says it looks like this. Omega gets selected here, or and that factors into the choice of alpha and beta, which determine theta and determine the individual hits and outs. Okay, and here's kind of just another diagram. Omega comes from this hyperprior, which is a beta. That determines what alpha and beta are, along with k, I should say, and that becomes our beta prior distribution. And that determines theta, the theta values, and the theta values go into Bernoulli's to determine the sequence of zeros and ones. Okay, so far that's what we have. And if I go back to Monday's lecture, what we had to do is we had to kind of break apart the joint distribution of everything into a whole bunch of conditional distributions. And we had to think about the posterior distribution. And so the posterior distribution that we would sample from is going to be the beta of alpha plus the number of hits, and beta plus the number of basically misses or outs, okay, where KS is the sum of the sequence of zeros and ones. Okay, and it worked though. When we did it ourselves, we simulated some data here. We had the number of at-bats, and we set up the kind of our hyper parameters of A omega, B omega, K, and then we said those will determine our hyper parameters alpha and beta. We're doing a mix of Gibbs sampling and Metropolis algorithm. So for the Metropolis algorithm, we're running Metropolis algorithm for the parameter omega, or I guess the hyper parameter omega, and Metropolis algorithm also requires a way to kind of evaluate our probabilities, and so we have a proposal function and a way to evaluate the probability. And so this is our loop to perform the Gibbs sampling. Gibbs sampling, we're conditioning values of theta drawn from the beta distribution, okay, the conditional beta distribution. And then values of omega will be used, uses the Metropolis algorithm where we propose a value and we either, and we calculate kind of the acceptance ratio, and we either accept or reject that. And so we get the omega values show up down here. Okay, so that runs, and we can say, all right, what kind of values of omega do we sample? And we see we get all kinds of values all over the place here. Here's kind of a histogram of the omega values, and we can also ask, you know, what are the quantiles? And so the 50th percentile for omega is something around 0.281. That's going to be the mode of our prior distribution. So when we created our prior distribution, when we selected it arbitrarily, we said alpha is 81, beta is 219, and you know, then that creates a mode of around 0.268, you know, around 27%, something around there. And you know, if we sampled, if we perform Gibbs sampling, you know, we get omega, 50th percentile of omega to be around 0.28, but omega could be as low as 0.26, as high as 0.301, something like that. So we're treating the selection of alpha and beta in our prior distribution to be kind of random variables. All right, and so that's what we did on Monday, and it works. Okay. Today I want to introduce JAGS. Okay. JAGS is a system, or is a program that can perform Gibbs sampling. And an advantage of using JAGS is that you don't have to go through the work of factoring out the joint distribution into a whole bunch of these little individual conditional distributions. Okay. Instead, all you have to do is specify the model. Okay. You specify the model, the hierarchical model, or whatever model you have, and then JAGS will figure out how to draw samples from this for you. Okay. JAGS is called Just Another Gibbs Sampler. It's based on the BUGS modeling language. BUGS was Bayesian inference using Gibbs sampling. And the way it works is you have to download and install the JAGS program. You download and install the JAGS program, and then you will interact with JAGS using your computer. Okay. And so, so there's an interface between R and JAGS, and there's a couple packages, couple libraries. There's RJAGS. Here we're going to use R2JAGS. But yeah, if you have Python, you can have Python interact with JAGS and things like that. There's another program called STAN that was recently developed. I don't know about recent, but more recently, I guess. And STAN also works, but here we'll look at JAGS. Okay, and so JAGS, you specify the model for JAGS using the BUGS language. Okay, the BUGS language looks like R. BUGS was written by an R user, so it looks a lot like R, but there's enough distinctions that that you'll want to kind of consult the documentation. So, so if you look at how to specify the BUGS model specification language, so it's got a bunch of these plate diagrams and stuff, but you can say, I want to use the Bernoulli distribution or the binomial distribution or exponential distribution and things like that. Okay, so all of these distributions are kind of specified and show you kind of the names of the parameters. So some of the names of the parameters are a little bit different from what we're accustomed to. So for example, the gamma distribution, we normally have shape parameters A and B, and but here it calls it R and mu, but this is what we have here. Okay. Okay. So again, if we look at just our hierarchical model, we have omega coming from a beta distribution. Omega determines alpha and beta, along with another parameter k. And alpha and beta determine our prior distribution. The prior distribution determines kind of the values of theta, and then the thetas get used in our Bernoulli to create values, zeros and ones here. Okay, so this is how we would write our model, our hierarchical model in the bugs language, okay? Now, in R, you wrap the entire model inside this function, okay? This is not a real function. It looks like I'm trying to write an R function, but if you look at it closely, because this looks kind of like R code, but it's not. If you try to run this function in R, it's going to error out, okay? Because this is not like a real function. But this is how we specify our model, okay? So within our model, and we kind of reference the data that we have, and so we're going to say we have a total of n players, and each player is going to be called S. Okay, so for S in 1 through n, the number of players that we have the player's batting average, theta subset to S. So player S's theta value comes from the beta distribution. Okay, and we're going to say this comes from d beta, the beta density here. And the parameters that define the beta density are going to be alpha and beta. Okay, now this is different from R's beta density function, because R's beta density function takes in shape parameters alpha and beta, but it's always asking what's the density of some value x. So you'd plug in like what's d beta of like 0.05 or something like that. Okay, but here we're just kind of specifying that this is a distribution. And we're using the tilde here to say that this random variable comes from this distribution here, okay? So again, not quite the R language. This is the bugs language, okay? And then once you have each player's theta value, theta sub S, or subscript subset to S, then we can talk about the values Y, okay? So inside R, we simulated a matrix of zeros and ones, and so Y is this big matrix, 10 rows, 521 columns, and so if I just take like the first row, and let's look at maybe like the first 200 values, all right, we have a whole bunch of zeros and ones. Okay, so this is what the maybe one of the rows in Y looks like. And so what we're saying is that as far as, for player S, so if we're looking at player 1, look at inside Y, row 1, and each position J, so J goes from 0 or 1 to the number of at-bats, each one of those comes from the Bernoulli distribution, right? And the Bernoulli being a distribution that produces a 0 or 1. So we're saying each value in our data comes from a Bernoulli distribution. And that Bernoulli distribution has probability parameter theta S, which is that player's batting average, okay? And there's actually no Bernoulli distribution function in R. So this is unique to the bugs language, okay? And so we have this. Does that kind of make sense as far as this part goes regarding specifying where theta is coming from? Theta is coming from this beta distribution, and the values Y are coming from the Bernoulli, right? So it lines up kind of with this picture here. Theta comes from the beta distribution, and once you have theta, the values of Y come from the Bernoulli. Okay, so one thing to note is that we actually never defined alpha or beta, and those get defined down here, okay? And so, but it's okay. So we're gonna say omega is a random variable. Omega is a random variable in that we've got this tilde here, and it comes from the beta distribution with parameters a omega and b omega, okay? And A omega is set to 3, B omega is set to 3, okay? And then alpha is set to be omega times k minus 2 plus 1, okay? Notice I'm using the traditional assignment operator here, indicating that there is no kind of randomness associated with these things, okay? Omega is a random variable. Omega is a random variable, and that's why we have the tilde here. But once omega is determined, whatever number omega turns out to be, then alpha and beta are set, okay? So, you know, alpha and beta are depend on this random variable omega, but the formula for getting alpha is fixed, okay? And then these are just arbitrarily selected, and these are also just fixed values, okay? I know it can be a little bit disorienting in that I'm calling for things like A omega and B omega, and I don't define them until here. And I'm calling for alpha and beta, and I don't define them until down here, and things like that, okay? Yeah, if in a traditional R program, these types of things would cause issues that we're asking for variables that haven't been defined yet. But as far as JAGS and the bugs language go, you're just kind of describing the thing, and it's going to read through the whole thing before it tries to start plugging in values. So it's going to read through it, and it's going to say, okay, these things are defined. It's fine that it's defined down here. And then and it's going to go through and it's going to figure out kind of the dependencies and the relationships between each of these variables here. Okay, and so so I wrote a couple slides on just kind of each individual thing here. So again, the model gets wrapped up in kind of a function here. You can also write a separate text file where you just specify, you know, you have a text file with just this, so you don't have to write it in a function. That's also possible, but then you have to kind of load in that text file. And then, yeah, we said for each player, we've got a theta value. Each player has a theta value. And then within each player, we're looking at the individual hits and misses, the zeros and ones here. Okay, and the omega comes from the hyper prior with hyper parameters. The hyper parameters are just kind of arbitrarily determined. K is arbitrarily selected. And these hyper parameters, alpha and beta, depend on our the other values, omega and k. All right, so let me show you this inside R. Okay, so we've got kind of the same. So this is the same simulated data from before, and so here let me just show you. Here's the model being specified. This is what I've written. So we've got theta for each player S, and then each individual outcome Y, which is this kind of sequence of zeros and ones for each player. Omega comes from the beta, alpha and beta are determined, and we have all of this. Okay, so we write that. Okay, and again, this is not a real function. If I tried to run this, it's going to get angry with me. Okay, and then when you want to run JAGS, okay, so again, JAGS is a separate computer program, but R will send information over to JAGS, and then it will run and it will get the information back. So when you want to make a call to JAGS, you have to give it a few parameters. You have to tell it the data that's going to be used. So if we look at our model specification here, there's a few things in here that are not defined, right? So I reference number of players. Okay, number of players is not defined inside of here. Number of at-bats is not defined inside the model, and neither is Y. Okay, everything else, all other variables are kind of defined inside of here. Okay, and so the data that this model is going to need to make use of will consist of my matrix Y, the number of at-bats, and the number of players. And so these are all variables that exist in my global environment. I've got the matrix Y, I've got the number of at-bats and the number of players. Okay, those were defined up here when we simulated our data. Okay, so I'm going to create a list of character names. So this is just how JAGS takes into its thing. You just give it a list of names, of character names, and then the JAGS function will say, oh, okay, I know to look for objects with these names inside the global environment, and I'll send them over to JAGS. Okay. We have to also tell it basically what parameters that we're going to keep track of. Okay. And so inside our model, we want to keep track of theta, which is the players' batting averages. Okay. So theta is going to be a vector of length number of players. Okay. So vector of length 10. I've got 10 players in my data. And then we also want to keep track of omega, which is the kind of the peak of my prior distribution. So here Bayes model parameters is going to be a vector of character names that of things to keep track of. And every variable that we want to keep track of in here, we also need to give it some initial values. So I have Bayes model initials. And this is going to be, again, it gets wrapped up in a function, but it's just a list, okay? And so, and it's going to be a list where the names is going to be just some random vector here, okay? And so in this case, my random, it's important that when you specify the random values that go into this thing, that it's compatible with the thing here. Okay, so in our case, theta is a vector of length 10, so this initialization needs to produce a vector of length 10. So I'm going to say r beta number of players, which is length 10, and I just have some arbitrary kind of starting parameters here, and that's fine. But as far as this goes, I need to use kind of the distribution r beta as far as random values of theta, because it has to be values between 0 and 1, right? Like if I try to give the model a theta value of like 2, it's going to error out, or a theta value of -1, it's going to error out. So if you get some kind of error, check to see if your initial values that you're using make sense, right? So this is something that people can miss easily, where you say like R norm and it gives you like errors and stuff. Okay, so those are the things that get passed into the JAGS function. You can also say, I want you to run 3 chains with this many iterations, this many burn-in values, and then the model is specified in Bayes mod, which is the name of our function here. Okay, so I'll go ahead and run all of this. Okay, so I'm going to go ahead and run the call to JAGS here, and it runs. Okay, and now it's done. Okay, now depending on how complex your hierarchical model is, JAGS can take a long time to run. JAGS actually has some features to take advantage of multi-core computers and things like that. And you know, if you go online, there's a lot of resources or a lot of tutorials and stuff talking about JAGS, so you can kind of look up information on how to get it to run faster and how to optimize all of this. You're just getting like this very, very, very brief intro to JAGS. We could probably have an entire course centered around Bayesian modeling and stuff. Okay, so anyway, we run that, and we can take a look at the resulting model. So we store the output of JAGS into Bayes mod fit. Okay, so Bayes model fit, and I print this out, and this is the results. And so here, there are 11 parameters for me to keep track of, right? I've got 10 theta parameters, 1 for each player, and I've got the omega parameter, which is the mode of my prior distribution. And so this is what it outputs. Okay, and so I've got you know, so omega goes from 0.261 all the way to 0.301 with a 50th percentile of around 0.281. Okay, and let's just compare that to the Gibbs sampler that we wrote ourselves. So we wrote our own Gibbs sampler. And when we wrote our own Gibbs sampler, we created a whole bunch of values, okay? And so we sampled a whole bunch of omega values. And so the values that we sampled from our Gibbs sampler, the omegas that we got, our 2.5 percentile is 0.260, and that lines up right accordingly here, 0.261. 25th percentile, 0.274, and here we get 0.273. 50th percentile, 0.281. 75th percentile, I have 0.288 versus 0.287. 97.5 percentile, I have 0.301, and here I got 0.301, okay? All to say is that the results of JAGS and the result of my own Gibbs sampler that I coded up kind of manually over here align. And that's a good sign, right? Anytime you do kind of attack the same problem from kind of two different methods and you get the same answers that agree with each other, that's a good sign. So I guess we can be confident that JAGS is sampling these values correctly, okay? Even though we didn't tell JAGS how to kind of factor it out into individual conditional distributions, it seems to still be sampling the values correctly here, okay? And I would say JAGS is very trustworthy. And in fact, if there is a misalignment between my results and JAGS, I would question whether I made a mistake somewhere else, okay? And I could also, inside, when we coded this ourselves, we can also look at the results of the players. And so player one, so if I compare the results of the JAGS fit, I can look at the results for player one. Player one had 118 hits out of 486 at-bats for an empirical batting average of 242.7, 0.2427, or 2.2428, okay? And here we can see what kind of values got sampled from JAGS and what kind of values got sampled from our Gibbs sampler. So for our Gibbs sampler, the 50th percentile is around 0.258, the 25th percentile is around 0.247, and the 2.5 percentile is around 0.227, and the 97.5 percentile goes up to 0.290. So these are the results up here. And if I look at theta 1, 2.5 percentile, I have 0.225 versus 0.227. 25th percentile, I have 0.247 and 0.247. 50th percentile, 0.258, 0.258. 75th percentile, 0.268, 0.269. And then 97.5 percentile, 0.289 versus 0.290. Okay, so I have very similar values here for the theta values of player one. Okay, and so on and so forth. You know, I could look at player two. Okay, player two had a few more hits and at-bats, 139 hits out of 493 at-bats, and their empirical batting average is around 0.281 or 0.282. Their empirical mean is 0.282, and the 50th percentile is also at 0.282, and that's what we have here also. For theta 2, we got 0.281. The 75th percentile, I got 0.292 versus 0.293. 97.5 percentile, I got 0.315 versus 0.315. So we're getting very similar results between the results of JAGS and kind of our own Gibbs sampler that we had to design by factoring everything out, all the conditional distributions accordingly. All right, is that okay? Seeing the results there. Let me give you some quiz answers. I've given you 0, or how many have I given you? None? I don't know. Okay. All right, well, I'll give you the first two. First two quiz answers are A and C. A as in apple, C as in cat. Your first two quiz answers for today. A as in apple, C as in cat are your first two quiz answers for this week. Okay, A and C. All right, so let's keep looking for JAGS. Well, this is just kind of going over the results. Oh, so there are plots that we can look at. Okay, so we can look at just kind of the results. You can also look at this is the plot that you get, and I'm not sure what this stuff up here is, but here it kind of creates confidence intervals for the different parameters that we're tracking now. So this is like an 80th percentile, 80% confidence interval. And here are 80% confidence intervals for the 10 different theta values that we have for each kind of player. You can create a trace plot. And so here is a trace plot for omega. And it just looks like craziness here. But this is actually what we want to see, okay? There are 3 chains that are being plotted. We have a green, a blue, and a red chain that are being plotted in this trace plot. And what we want to see is a trace plot that looks like the values are sampled independently, okay? Because that's ideally what we want. Now, and the way this Gibbs sampler achieves values that look like they're sampled independently is that it kind of samples a whole bunch and it throws a bunch of them away. And so the ones that remain look like they are independently sampled. Now, if you can trace some kind of path through the trace plot, then that's a bad sign, okay? So, but right now we're getting values that look good. Here's a trace plot for theta 1. And again, no discernible patterns here. So, so this is a good sign, right? So basically, if you see a pattern in your trace plot, that's an indication that something went wrong. Okay, so we've got a trace plot for basically every single variable that we did, and so so there's a whole bunch of these things. But you know, here's for the 10th player, trace plot of their theta values. Okay, there are other kind of diagnostic plots that you can fit. They require loading up other libraries, and it actually requires the results of our JAGS output to get modeled into this MCMC style output. Okay, but based on that, you can create a plot. Excuse me. So we have a whole bunch of trace plots. And again, what we don't want to see is any kind of discernible pattern in the trace plots, and it doesn't look like there is one. And we can also look at a density plot, which shows the resulting densities of all of the different kind of parameters that we're looking at. I don't know the order in which how these got plotted, but here we have kind of the density for theta 1, and we can see it's centered around, looks like 0.26, something around there, 0.25, 0.26-ish, something around here. And these are kind of the density plots for the 3 different traces. And what you want to see is that all 3 traces produce similar density plots, and overall they do. And here it also shows that, you know, each density plot's a little bit different. So theta 1 is centered around, looks like 0.26, whereas theta 2 looks to be centered around 0.28. And theta 7 is centered around, it looks like 0.31 or something like that. Okay, so depending on the player, different players have different batting averages. And so, you know, if we look at, say, player 7, okay, player 7 has had the kind of greatest success here, with an empirical batting average of around 0.325. And so, you know, after we kind of factor in, you know, overall, it would probably be really hard for this player to maintain this kind of batting average of 325 throughout the entire season. So, you know, we kind of adjust down to say, you know, player's batting average probably around 0.309, but it could be high, like 0.321. And in the 97.5, we go, you know, even so far as high as 0.343. But on the low end, you know, the batting average could be as low as 0.278 or something like that. Okay. So you know, if we look at that, so if we look at kind of the density plot that we have for player 7, you know, it's centered around 0.331, okay? And this is kind of what we got when we did our own manual Gibbs sampling. Our results align as well. Okay, so that's those are some of the plots that you can get from that. You can use the sampled values. You can access them by looking at the results of inside Bayes mod fit. If we look at the structure of this, it's just that it's this big list. All right. So if I say, what's the structure of Bayes mod fit? Oops. Okay. It's a big list. It's a list of 6. We've got the model, the bugs output, which is a huge list in of itself. And then we've got a bunch of kind of the parameters to save, the model file, and all sorts of stuff like this. Okay, but so inside this, the kind of the most important element inside the output is the bugs output. And within the bugs output, it contains a bunch of information about the chains that were run. It says there were 3 chains, 15,000 iterations, this many burn-in periods, and stuff like that. And then the values that it simulated get stored in Sims list. Okay, Sims list here. We want to look at the omega and we want to look at the theta values. So if you look at Sims list and the variable theta, because there are 10 theta values that we kept track of, okay, the 10 theta values, we're going to have a matrix, a 3000 by 10 matrix. And so, so this is what we have. And so we can access those directly by just saying, I want from the model, let's look at the bugs output. Let's look at the simulated list. And within the simulated list, let's look at the variable theta. And here, I just want the first column. Okay, the first column will be the theta values for player number 1. And so I'm going to store this this will be sampled values for theta 1. And here we can see a histogram of the sampled values of theta 1. Okay, and we can use these sampled values of theta 1 in Monte Carlo estimation. All right, so I could ask a question: what is the probability that player 1 will get 2 or 3 hits in the next 10 at-bats? Now, again, the frequentist approach would be, you know, let's just use the maximum likelihood number, and we're going to say player 1 has a batting average of, you know, 0.26, and we're going to plug in 0.26 and get our numbers. Now, the Bayesian approach says, well, we don't want to specify that theta is one exact value, and so we're going to allow theta to be, you know, any number as low as 0.20, as high as 0.32, but definitely we're going to put stronger emphasis on the values near 0.26, 0.25, 0.26, 0.27. Those are the most likely values. And so we're going to kind of we're going to put those numbers in here. Okay. And so so we do that. So we create our function h, and h is going to be d binom 2, 10 using theta plus d binom 3, 10 using theta. And then to get kind of our Monte Carlo estimation, we take all of our sampled values of theta that we, you know, the values that we've generated using Gibbs sampling, and we'll plug them into H, and we'll get our mean. Okay, so it's very similar to what we did. You know, I think we did this way back in like week 2. Okay, but back in week 2, the way we got our sampled values of theta was we used our beta function, right? We knew the posterior distribution for this one player, and we sampled them, and we did our beta. And now we've got, you know, a slightly more complicated model, and so we're using Gibbs sampling for all of this, but we still generate sampled values of theta that we can then use for Monte Carlo estimation. Okay, so all of this work, all of this talk about Markov chains and all of this is just so that we can basically do the same thing that we did, you know, way back in week 2, but for situations where maybe we can't just use R beta to generate all of our values. Okay, and so I know it was like weeks and weeks and weeks of all of this stuff of random number generation, but a lot of times we have situations where you have some kind of model and you're not quite sure what kind of values that we can use, especially because there's kind of there's dependencies between you know, what values of alpha and beta that we choose and all of that stuff. Okay, so anyway, this is how we can use those things. Let me just show you some modifications that we can make to the JAGS model. So let me compare this. So in slide 10, we are looking, the data that we're looking at are the individual hits and outs, right? So we're looking at matrix Y, and let's say we're looking at these zeros and ones. Now what we can do, instead of looking at the individual hits, I have my vector. Did I not do that correctly? I have to do row sums. If I do row sums of the hits, I can take the, you know, the sum of all, you know, however many values were in that row, and I say, okay, there's a total of 118 hits, okay, for player 1. Player 2 has a total of 139 hits, okay? And so this time when I specify the model, rather than looking at individual hits, zeros and ones coming from Bernoulli, and having a loop going over each at-bat, I can just kind of, I can do this, right? I can simplify my model a tiny bit, and I can say the number of hits, so Y now represents the total number of hits, comes from a binomial distribution. Okay, so the total number of hits come from a binomial distribution with parameters theta S, which is the player's batting average, and the player's batting average and the number of at-bats here. Okay, here N represents the number of at-bats. And the player's batting average comes from the beta distribution with shape parameters alpha and beta. Everything else is the same, okay? Omega comes from this beta distribution. Alpha is determined by omega and k. Beta is determined by omega and k. And this omega has these hyper parameters, and k is also a hyper parameter that we just specify. But is that all right that this change right here, where I've, rather than modeling the individual at-bats, whether it's a 0 or a 1 as far as a hit or a miss, now I'm modeling the total number of hits, or modeling the total number of hits Y. Okay, and so I can do that right here. I just change, wait, no, that's model 1, or I'm looking at the individual. So here we've got Y. Y represents the total number of hits, and so we specify it right there, and we can just run the same thing, and it gives me pretty much the same results. Okay, I can run through this. I get like the same results. So these results are going to be pretty much the same. Okay, so that was just one change here, and I'm going to do one more change, and that is I'm going to, so right here, this model says K, which determines what alpha and beta are in this prior distribution. K was just arbitrarily determined to be 300. Now, we might not be comfortable using K to be arbitrarily chosen as 300. And so we can say K itself is a random variable, and we'll put a hyper prior distribution on K. And so I guess a hyper prior on K. And so K, rather than just saying is 300, I'm going to, you know, and this was arbitrarily chosen, okay? So at some point you probably have to arbitrarily choose something, but the more generations back you are removed from the data, you know, the less influence your choices make. So here I just chose this distribution, this D gamma distribution with shape parameters 2 and rate parameter 0.008. because this creates this very wide, super long-tailed distribution where, you know, values between, say, 50 and 500 have high probabilities, but, you know, it could go, K could be as high as like 1,000 and something like that, but K is also unlikely to be a value like 1 or 2. Okay, so this just says, you know, any values for, say, from like 50 to 500 are kind of have high probabilities. If you wanted to say, you know, K comes from a normal distribution centered at 300 with a standard deviation of 100, that would also be fine, right? So you have a normal distribution centered at 300, goes, you know, goes down to 0, goes up to 600 type of thing. You can also specify that for what K could be. In that case, you would need to, in the bugs language, you can use an I to indicate that you know, if it falls below 0, then it's not allowed. Like a normal distribution technically goes from negative infinity to plus infinity, and you would run into problems if your K variable became negative. So anyway, here I'm just saying K comes from this gamma distribution. This is very arbitrary, but again, what it does is it allows K to be a random variable. All right, and so to specify this, I keep everything else the same. We're going to model the total number of hits. Theta is the player's individual batting average. Omega is going to be coming from the beta distribution. And now K comes from the gamma distribution. Okay, and so if I do that, now I have to specify, I have to make a change to this. As far as the model parameters go, I need to include K as one of the model parameters that I'm going to keep track of. And because I now have K inside my model parameters, I need to include a way to initialize it. Okay, and so here I'm just going to say pick one random value for K for the initial settings here. So we have to initialize this. Okay, and now I can run this, and we're going to get the results here. And so as far as looking at the results of this model fit, now we are modeling also K. And so the 50th percentile for K is close to 300, 297, which aligns kind of close to the values that we saw. But it says, you know, K might be as small as 100, might be as big as 740. And so as far as what KU value we use as to determine the shape parameters alpha and beta in our prior distribution, we can model this using a random variable as well. Okay, so this is so I think JAGS is quite a powerful tool, quite a useful tool in that all of these things is we can make changes to the structure of our hierarchical model without having to factor everything into all of these conditional distributions, okay? Because factoring them into the conditional distributions, you know, it's possible, but it's not easy. Whereas JAGS makes it real easy for us in that we don't have to do it, okay? JAGS, we specify the structure of the model, the hierarchical model, using kind of the JAGS language, which, you know, it has its own quirks and takes a little bit of getting used to. But once you specify it and you set up kind of your parameters accordingly, you can then draw samples from it, samples that we can then use for Monte Carlo estimation and things like that. There's lots of resources online. If you're interested in this, you can just go on Google and type in using JAGS and R and things like that. Okay, we'll end here. Let me give you your last quiz answer. And I think also, and I have to, so your last quiz answer is E. E as in elephant. E as in elephant is your last quiz answer. Okay, I have a favor to ask of you guys, and that is I think you'll get instructor evaluations and course evaluations and things like that. And so I would like for to ask that you guys fill those out. Those are helpful. I'm actually scheduled to be reviewed for a promotion this year. So your course evaluations and things like that get factored and considered in there. So so yeah, thank you. So anyway, I hope I hope it goes well. But and I hope you enjoyed the course. I hope you you know, I wish we were in person. I very much enjoy the face-to-face interaction, but I appreciate all of you guys being here, especially those of you who turned your cameras on, and even those of you who didn't turn on. I appreciate you just seeing your names listed that you came in here, and even if you're not live, thanks for watching on YouTube and stuff like that. So anyway, I hope you like the course. If you have feedback, if there's anything that you think I could improve, anything you didn't like, don't hesitate to write those down as well. Specific feedback is always more helpful. So rather than saying like, this was confusing, the class was confusing, it would be more helpful if you could say, you know, the way you covered, you know, this topic, lecture 7.1 and 7.2, I had trouble understanding this or things like that. Then I know, okay, I can go back and I can review what I wrote in those lectures and make changes and things like that. So anything, the more specific you can be, the more helpful it is. I know it's more work to be more specific. So, but anyway, please consider leaving me a review. I'll probably have to make the appeal again, but that's all. Okay, so we'll end here, and we'll see you guys on Friday. We'll take a look at more stuff. All right, have a good day, you guys.